Good afternoon. I am Mr. Ish. Thank you again for watching the videos. Thank you for subscribing. We have here a conclusion video for type 2 improper integrals. With regards to type 1 and type 2, we have sufficient background knowledge now that we can have and demonstrate a good understanding of this whole concept of improper integrals. We can state with a relative confidence that we can handle these type of integrals. Our first question, a very interesting question, will be this: 2 natural log x over x dx from 0 to 2. This will have an interesting other aspect which will come in, which we will talk about. Nothing related to improper integrals, but a useful tidbit information that we will talk about when the time comes. When you're looking specifically at this question, a graph demonstrates a x-intercept of 1, 0, a x-intercept, and it comes and it goes and it proceeds in that direction. It doesn't have to be 100% accurate, but the fact that we're seeing that there's no portion of this curve located in this side or the left of the y-axis, we know very well, or this interval can be written in this way: 0, 2, including 2. Writing it in this form kind of helps you out in writing the limit. You know there's a single right hand limit which will come into play, and it will be something like this: limit as t will approach 0, but from the right we will be looking at t to 2 ln x over x dx. And what are we looking at here with regards to the area of the curve? Here's my 0, here's a 1, here's a 2. We're looking at all of this possible area which is located above the curve, and then all of this area which is located below the curve, and this right here is my 2, 0. And that right there clearly tells us, well, maybe not clearly, but it gives us an idea that we may have a divergence at play, but we have to show that to be the case by means of this procedure. Anyhow, let's come back to our question. If you take this 2 and you push it aside and outside, and we can bring it right outside our limit, this is exactly what we're looking at here with regards to our integral. The 2 has been pushed outside. It's a coefficient. You can push it out. When you look at this, you have to obviously erase this because we can't double count the 2. But when you look at this, you really are looking at it ln x and times 1 over x dx. In rough representation, you're looking at an f of x and its derivative in terms of an integrand, a product of two functions. One of which is a function, one of it is its derivative. At any point you see something like this, always go to this form in terms of your antiderivative, which would in this case be ln square x over 2 plus c, but this 2 will cancel out with this 2 sitting out. Anyhow, why is this the case? Because anytime you have an integrand which is made of a product of a function and its derivative, it will always, by means of polynomial substitution, go down this path. When you resubstitute your u, you'll get ln x. This is a unique integral shortcut, and I've presented this in a video. I'll add a tag to that video in the information for this video. It's a unique integral shortcut that you should be aware of. A function times its derivative, serving both as an integrand, always goes into that u square over 2 format, or your original function squared divided by 2. If you didn't know that, you have to use polynomial substitution. U is equal to ln x, du is equal to 1 over x dx, dx is equal to x du. Bring everything into this play. You have u du x over x, and this cancels out, and you end up with u square over 2, and then you end up with ln square over 2 x plus c. You see how you ended up with u square over 2, and that's exactly what I'm talking about. A function and its derivative serving as an integrand will always develop this form right here, and in its finality you'll always have something which will look like this. It's a unique integral shortcut you should always keep in the back of your mind. Anyhow, we've now demonstrated what the antiderivative is, and let's bring that into play from this point onwards. We have a limit as t approaches 0 from the right. We have now the antiderivative ln square x over 2, right? And then we have an upper limit 2, lower limit t. What I'm going to do now is very well remove the 2's. A denominator 2 and numerator 2 cancel out very well. You have 2 coming in and you have t coming in, and the difference of the 2. And let's see how that plays out. You have ln square 2 minus ln square t, right? What does this become? Well, this right here is going to be the problem when the t gets placed with that 0, which it really is. Ln square 2 is a good finite number, but this right here is going to give you a minus infinity, and you know there's a square, and that right there will give you a divergence as your answer. Why is this generating a minus infinity? Because for any natural log curve having a 1, 0 x-intercept and coming from this direction, from the right towards the left towards your vertical asymptote, which is x equals 0, your function dips down here towards minus infinity. So limit as this t approaches 0 from the right, you're dipping down towards minus infinity, and that's what falls here. You get really a ln squared 2 minus infinity square, and technically your answer is just infinity over here. Whether it's positive or minus really makes no difference, but your answer here is an infinity, which you represent clearly as a divergence. And the reason why it is because limit as t approaches 0 from the right, you're approaching minus infinity, is not a true and it's not a good limit answer, because you want to have a good finite answer for a limit value. Generally you do. Anyhow, our answer here is D. D for divergence. This integral diverges and you cannot solve it in terms of the area which was involved with the interval and with this curve for this area. That area cannot be calculated due to divergence. This question number 1 for this video has been completed. This right here is our question number 2, but the previous question, as you notice, had an infinite discontinuity located with regards to the vertical asymptote at x equals 0. This will also have a good vertical asymptote. If you zero out the denominator, you know x equals 0 is a good vertical asymptote. But look right here at the intervals. You're having elements of type 1 improper integrals at play, and then you're also having elements of type 2 improper integral with this infinite discontinuity located within your interval. Your interval here is minus infinity to infinity, but right in between at this value of 0, you have an infinite discontinuity at play. So how do we handle a question which has elements of type 1 improper integrals and elements of type 2? Well, you look at what you have in terms of the graph and you weigh out all the factors, and then you make a decision as to which format or which type takes precedence. When you look at a basic graph of a 1 over x, which is your hyperbola, by the mere fact that you have a square here instead of an x, you have x squared, not an x, it takes all of these negative y values or range values and it pushes them upwards right here in terms of a positive y output. But then with regards to this x to the 1 and x squared, this pushes everything down seemingly such that you will zero out. How I've drawn it is not 100% accurate, but this right here distance would be much less. The distance between here and here and here and here would be much less than compared to 1 over x. This would zero out very quickly. Anyhow, we have this representation shown over here. There's something, before we do this question in terms of its determination, there's something we need to talk about. Let me bring you a better representation in terms of a graph. We're looking at something like this right over here. We have this x equals 0, which is your y-axis, and we're looking at everything here from minus infinity to infinity. Our interval, as you know, is minus infinity, but let me write it better. Minus infinity to 0, and then we jump across 0 up to infinity. That right there is my true interval. Now let me tell you something very important. There are 4 limits here at play. Limit as x approaches minus infinity, limit as x approaches infinity, limit as x approaches 0 from the left, limit as x approaches 0 from the right. Let's write them out. Limit as x approaches minus infinity, it's doable. You can calculate that. Limit as x approaches infinity, or this infinity, it's doable. You can calculate that. Limit as x approaches 0 from the left, and limit as x approaches 0 from the right. These both are not really doable in the true sense. As this x will approach minus infinity, your function will approach very close to this horizontal asymptote, which is y equals 0. In both instances, as x approaches minus infinity and as x approaches infinity, your function dips down towards this x-axis, which is y equals 0. And in both instances, you have a good finite value for your limit. Limit as x approaches 0 from the left, you exceed beyond bounds towards the direction of positive infinity. Limit as x approaches 0 from the right, again your function exceeds beyond bounds towards the direction of positive infinity. But technically positive and minus infinities are not good values for limits. They're not acceptable values. So when you technically have these, you can say a limit does not exist in the true form of the sense. So you have 4 limits, 2 of which are good and 2 of which are not good. The ones which are not good are associated with your infinite discontinuity. The ones which are good are actually associated with an infinite interval, which is what you would associate with a type 1 improper integral. The fact that both of these associated with the infinity limits are good, then that means the type 2 must take precedence, and you must treat this question as a type 2 improper integral, and that's how we must do it, because the infinite intervals actually provide you with a good limit value, and that's how we will proceed with this question. Again, you're looking in terms of the area of the curve, all of this right here and then going up, and then all of this right here and going up, and very likely you will see divergence, but we have to show that to be the case. Now that we've evaluated this to be a type 2 question, let's set our limit. we'll do limit as t approaches 0 from the left. You see how we're not bringing infinity here anymore. You can very well treat minus infinity as a good limit value right here. And then we're coming up to t, we have 1 over x squared dx plus, let's go to the other side of that y-axis. Limit as t approaches 0 now from the right. We will have here t, and then we're going up to positive infinity, 1 over x squared dx. You know 1 over x squared in terms of its antiderivative is easy. The antiderivative of 1 over x squared dx need not be mentioned in terms of work. We know it's just minus 1 over x plus c. That's what we have. Let's do all of this now in terms of its evaluation. Limit as t approaches 0 from the left, we have minus 1 over x. We can push the minus out. There's nothing wrong with pushing that minus out. We're looking here from t up to minus infinity plus limit as t will approach 0 from the right. We can again push this minus out. We're looking at 1 over x, right? Minus 1 over x. We're looking here from a t up to a positive infinity. Now we have the fun task of evaluating all of this in terms of the 4 limits I presented. But before we do, let me just tell you, in this interesting question right here, the tidbit or extra bit of knowledge we needed was to be able to demonstrate or differentiate. In this type of example, what would take more precedence? The fact that we have these infinite intervals, would we be thinking about type 1, or the fact that we have a infinite discontinuity here at play at this vertical asymptote x equals 0, would that take precedence? And in these type of cases, it's generally the type 2 which would take precedence over the type 1 aspect, because here specifically the type 1 intervals, these minus infinity and positive infinity, the limits are very clear and they're established. In both instances, the function would approach 0. Your x-axis, which is your y equals 0, as this function approaches minus infinity, as it approaches positive infinity, your function dips down towards that x-axis, which is y equals 0. The only limit that didn't exist was these ones right here, where x is approaching 0 from the left or from the right. You have that vertical asymptote at play. The function exceeds beyond bounds. Let's evaluate this part. You'll have the t and the minus infinity, the difference of the two. Here you'll have infinity and t and the difference of the two. If we have a minus sitting outside, we can keep it outside. We have 1 over t, and then we have this minus, then 1 over minus infinity, plus. We have this minus again sitting outside. We have 1 over this upper limit infinity, minus 1 over t, the lower limit here, t. In all instances, the t here represents 0. So now let's bring 0 into play, and let's take this plus and minus and convert it into a minus. When we bring in these zeros in places, that's what creates a problem. 1 over 0 is undefined. It creates a divergence. But 1 divided by minus infinity, limit as x approaches minus infinity, we know this function specifically approaches 0. You're doing such a large number on the denominator, large in terms of this quantity, you always will zero it out. Likewise, 1 divided by infinity will zero out. This function will approach your x-axis as it approaches infinity. From this point here, it's relatively straightforward. You might as well just discount the zeros. You got minus 1 over 0 right here, coming from right over here. You have a plus 1 over 0. You cannot think of minus 1 over 0 and plus 1 over 0 as minus infinity plus positive infinity and they cancel out. It doesn't work that way. In terms of what we have, this integral evaluation we have to do, this really represents a value that you would say that your integral diverges, and you couldn't do a good determination here of the area which was affected by this function in terms of the interval that's provided. Your answer here is that this function is experiencing divergence over this, or you can say simply the integral diverges. Don't really make the mistake of doing minus infinity plus infinity, you cancel them out. It doesn't work that way. If you have a divergence at one part of your interval, then you really have a divergence over the entire part of that complete interval that we have from right over here all the way here, with this infinite discontinuity at play. What basically spoiled it for this specific function is this infinite discontinuity. Limit here at x approaching 0 from the left and right did not exist, and that spoils it. Gives you this good answer here of divergence or diverges. And don't make these mistakes over here with regards to these specific or part or small part of intervals and then doing like a negation of a positive and a minus. You don't want to do that type of an error. Anyhow, long story short, this answer here is very well good. Divergence, diverges. You cannot go wrong with that. This question has been completed. The previous question was done. They both incidentally led to a good answer here of D, divergence. With that, I thank you all for watching these videos on improper integrals. Stay tuned. If you have any questions, leave them in the comment section. Thank you for watching. Have a nice day. Bye.